In this section, we're going to talk about strong acids and bases. A strong acid, and by extension a strong base, are those species that completely split apart when they are placed in an aqueous solution. So they ionize completely and nothing of the original base or acid is left in solution. So they ionize completely. So let's take a look here at an example. If I have HCl and I put that in water, that means that the hydrogen, so the HCl gives up the proton to the water, it donates the proton. All of the HCl splits apart, and leaving me with Cl- and H3O plus ions. So if I were to zoom in, if you will, into that aqueous solution of HCl, and I were to look for what species I have in solution, they will all be either hydronium ions, H3O plus, or chloride anions, Cl-. There will not be any HCl left in solution. All of it splits apart, and that is because it's a strong acid. Same thing with a strong base. The strong base completely dissociates and none of the original compound remains. So here's an example of that. I have NaOH. When placed in water, is going to split into Na plus and OH minus. And there's no NaOH left when it's placed in an aqueous solution. We can then calculate the amount of H3O plus and OH minus in aqueous solutions of strong acids and strong bases, because when we have a strong acid, like we do here, for example, we know that the H plus concentration is going to be the same as the concentration of my acid, because HNO3 is completely going to dissociate into H plus and NO3 minus. I do this example with my classes all the time, and I know it's kind of corny, but if you were to go to a dance and you had 10 couples, kind of like your acid here, you had 10 couples, and at the end of the dance, they split because there's a break, and the boys are going to go on one side and the girls on the other side. Well, how many boys and how many girls are you going to have if the couples completely split apart, just like the strong acid? Well, you're going to have 10 boys and 10 girls because you had 10 couples. Same idea here with how we figure out the H3O plus concentration in a strong acid solution. The H3O plus is going to be the concentration of my acid if it's a 1-to-1 ratio, right? Here I have one hydrogen for my strong acid. I have one hydrogen for every molecule of acid, so it's going to split apart to give me that concentration. Once I know the H3O plus concentration, I can calculate the OH minus because I know that the product of these two concentrations is 1 times 10 to the minus 14. And here it is. So I know the product of these is 1 times 10 to the minus 14 at 25 degrees Celsius. So I can rearrange then for the OH minus concentration to 1 times 10 to the minus 14 divided by the H3O plus. So for H plus, they're going to be equal to the concentration of the acid. For the OH minus, you have to solve by dividing 1 times 10 to the minus 14 by the acid. Let's take a look at the same thing, but now we have base, so strong bases, not acids, and we have to calculate the OH minus and H3O plus concentrations. Now, I'm going to do A for you because it's slightly a little more difficult. These are pretty easy because they split just like the acids, and the OH minus is equal to whatever the concentration of the base is. But for this one, not quite, because we have twice as many OH as we do calcium hydroxide. So when we put calcium hydroxide into water, it's going to split like this. It's going to give me one calcium 2+ ion plus 2 OH minus ions. It's a balanced reaction now. So to calculate the OH minus concentration then, I have to take into account that I have twice as many OH minus ions as I do calcium hydroxide molecules. So the calcium hydroxide concentration is 4.51 times 10 to the minus 5, but the concentration of OH minus will be twice as much. So I have OH minus is equal to 2 times the 4.15 times 10 to the minus 5th molar, giving me 8.3 times 10 to the minus 5 molar concentration for OH minus. Once I know the concentration of OH minus, I can solve for H3O plus, because I know that the concentration of H3O plus is equal to 1 times 10 to the minus 14 divided by 8.3 times 10 to the minus 5, giving me 1.2 times 10 to the minus 10. Note that I assume, it wasn't given to me in the problem, but I assume that it's at 25 degrees Celsius. If it isn't specified in the problem, then you will use this value for the product of H3O plus and OH minus concentrations. Okay, go ahead and try B and C on your own.